Hi, as we keep delving deeper into our trigonometry, here comes the next topic, which is small angle approximations. Let's say kind of trigonometry as you knew it. You saw a little bit extra in year one, but trigonometry as you knew it is now going to go bonkers as we get into all the year two stuff. There's a load more stuff that we're going to get into, and also a huge amount of stuff that we're not going to go anywhere near. Trigonometry is, let's say, a frighteningly large topic that pops up in every conceivable realm of mathematics. So we are still, though we're kind of expanding our knowledge, we are still just skimming the surface. But here we go. This is the next section on this particular set of kind of the basics, if you like. And we're going to talk about small angle approximations. So approximations for sine, cos, and tan. Now, before we do that, we're just going to jump back a little bit, and I'm going to talk a little bit about binomial expansion, which you did some of in year one, and it might be you've seen your knowledge of binomial expansions extended this year. It might be you haven't, in which case don't worry about it. I'm going to kind of skip briefly over it. But what we get is we can find that if we do an expansion of something like that, which if I wrote that as a power would be 1 plus x to the power of minus a half, as it turns out is we can approximate that by doing this expansion of increasing powers of x. And these terms keep going and keep going and keep going. And we can use these things to come up with approximations for the value of an expression. So, for example, if x is 0.1, if I put 0.1 into this fraction here for my value for x, what I'd find is we're doing that, and we get this value of 0.95. But the same thing could be done if I put it into the expansion, which is this thing here. You can see I've just put in those 0.1s, and what you get is a value that is pretty much the same. You can see it's the same to 2 decimal places. Well, technically I think 3 decimal places, but there's a slight difference. But what you've got there is this approximation here is a pretty good approximation for the actual value. Now, what we've got, let's say in this particular case, it was only 0.068% away from the actual value, which is, let's say, not a bad effort. Two things that are worth noting with this, and let's say you'll get more understanding and deeper understanding of this when you do this topic, when you do your binomial expansion stuff, is that the more terms you include, the more accurate it becomes. And the second thing, and the key thing, is this only really works when we're dealing with small values of x. Beyond a certain limit, these things no longer work. So those are just two things to bear in mind as we move on to the next bit. We can do something similar with trig ratios, although it doesn't use binomial. It uses something called a Maclaurin expansion, which is something that further mathematicians get to have a play around with because it's on the further maths course, not the maths course. And what we've got is you can calculate the sine of any particular value or any particular angle by using that expansion. And you can see it's quite a structured thing. We've got kind of goes x to the power 1, x cubed, x5, x7, odd powers. And then on the bottom you've got factorials and alternating positive and negative. So a really kind of structured thing. And I suspect this is how your calculators might go about working out trig values. Cos x looks like that. You can see again, same kind of deal. You've got that alternating positive, negative, positive, negative, but this time it's happening because with the even powers. Tan is a little bit more weird, but then again, tan always is. And so we've got increasing powers that are odd, but let's say the numbers on the bottom of the fraction are not quite as organised as they are for sine and cos. But long story short, those values there will give you approximations for the value of sine, cos, and tan. Now, what we're going to do is just look at what we get for those small values, and particularly just for taking the initial terms. And so the terms you need to work with, I'm just going to take the first term from sine, the first 2 terms from cos, and again the first term from the tan expansion. So what we've got is that the value of sine x is approximately equal to the value of x when x is small. And it's also it is absolutely essential to note that this only works in radians, it doesn't work for degrees. So we're talking small values of x in terms of radians. Sin x and tan x are the ones that are fairly straightforward. They're just sin x is approximately equal to x, tan x approximately equal to x, cos x a little bit more, it's approximately equal to 1 minus x squared over 2. And you need to know those things, and those are the things that you're going to be using and working with when it comes to solving problems. Just to give you a little bit more clarity on what's going on with those, let's just have a look at what happens when we plot values, when we look at the curves. What you've got there is the red curve is y equals sin x, and you've got the blue line, which is the line y equals x, and you can see that the blue line and the red line for small values, so I'm just looking at this section of the curve here, are quite similar. As it turns out, our blue line has got a gradient of 1, it turns out y equals sine x has got a gradient of 1 at the origin. But you'll notice you get to a certain point round about here where the blue line and the red line start to diverge. So that's the point I'm trying to illustrate there, being these approximations that only work, they're only similar for small values of x. Because of the nature of the cos curve, it is more pertinent to use a quadratic to fit the cos curve. So we've got this 1 minus half x squared, and again you can see for a range of values from about where my cursor is there, it's looking pretty much similar, and it starts to diverge again round about there. So we can use that quadratic to approximate our cos curve, and then finally is the tan curve, and again you can see y equals tan x has got a gradient of 1 round about 0, and again clearly there's a large divergence once you get beyond the range where my cursor is at the moment. Okay, so that's all the theory, that's what's going on. Let's have a look at how this is going to be used. So this might be the kind of question that you get in. So let's start off with our approximation. So we know that cos x is approximately 1 minus x squared, and we've got to adjust it because we want the approximation for cos 2x. So if I put a 2x in there, that means the 2x is going in there, which means I end up with that. Do a bit of kind of multiplying out the brackets and tidying up the fraction, and it ends up there. You might want to just pause the video and have a little play with that and just check you're happy with that. And if we do something with the bit on the bottom, which is the sine, so we know that sine x is approximately the same as x, so therefore sine squared 3x will be approximately the same as 3x all squared, which is 9x squared. Now we've done those bits, let's just pop them into our formula, which is, an expression up here. So we end up with 1 minus cos 2x over sine squared 3x is approximately equal to 1 minus this thing, all over 9x squared. Tidy it up, do some cancelling, and you can see that we get a value of 2/9. So what that's telling is, for any value of x, as long as x is small, the value of that expression will always be 2/9, or approximately 2/9. Okay, on we go. Different kind of question here. So what we've got is, for this triangle, show that the area is approximately given by that expression half x minus a quarter x cubed if x is small, and then find the percentage error between the actual area and our approximate area if the angle is 5 degrees. So off we go again. So we need to start sorting out, we need base times height, so we need the length of the base and the height of that triangle, and hopefully we'll be okay if we realise that the height is going to be sine x and the base is cos x. If you want to take a moment just to kind of figure those things out, those are results that you've seen before in a range of different areas, possibly particularly mechanics. So there's our base times height. So we know that the area of the triangle is half base times height, and it's at this point we can now do our replacements for cos x and sine x using our approximations. So we've got half cos x, which is the 1 minus x squared over 2. There's our approximation for sine x. Multiply it all out, and you end up with the result that we were working towards in the question. Okay, find the percentage error if the angle is 5 degrees, and I suspect if this came out of the exam, the majority of mistakes would happen would be because students would still think about working in degrees, because thinking, well, 5 degrees is not particularly big, but remember I said earlier, this is only applicable if we are working in radians. So we've got to turn it to radians, so 5 degrees is pi over 36 radians. And so now what one can do is take that pi over 36 and plug it into our formula. So this is finding the actual value. So that's our half base times height. So we end up with that value there. Quite a small triangle. And then let's do the same thing, but let's now bash it into our approximation. And we end up with a very similar value. And the question says, what's the percentage error? So percentage error is going to be the difference between our two figures, the difference between those two, and then divided by the original one. The original one is going to be that one there, the 0.43412. There it goes. And then finally turn that into percentage. You do the times by 100, and we end up with a 0.127% error. So again, a fairly accurate approximation for the actual area. And there we go. So all your questions on small angle approximations will be asking you to use our standard results. The one on the screen obviously is 10x is approximately x, and then just asking you to manipulate them in some way.